The representation theory of semi-simple Lie algebras is everywhere. Here we will introduce a large set of such representations that can still be studied well. The set is called the Berenstein-Gelfand category O. So we will assume some preliminary knowledge about semi-simple Lie algebras. Assume that the semi-simple Lie algebra has a Cartan subalgebra H. We moreover assume that you are familiar with the universal enveloping algebra, which consists of any linear combination of any number of generators. Moreover, I will assume that you are familiar with roots, weights, as well as the Cartan decomposition of the algebra. It looks as follows. G is the direct sum of algebras associated to the negative roots, the Cartan subalgebra, and the subalgebra N associated to the positive roots. Now, what we will study is a full subcategory of left modules of the universal enveloping algebra. We will not worry about defining some of the mathematical nomenclature that we use. For now, just think of it as representations of G, if you want. The subcategory that we study has three properties. Firstly, any module M is finitely generated over our universal enveloping algebra. That means that we can find some vectors in M a finite set, such that if we act with all linear combinations of all multiples of generators, then we will generate the whole module. Secondly, M is H semi-simple, meaning that M is a sum of weight spaces. So where lambda is in the dual of H star. So it's a possibly infinite sum of weight spaces. So H can be diagonalized in some sense. And thirdly, M is locally UN finite. So if we take a vector V element of M and we act with UN on V, then this is finite dimensional. This means locally finite. So how should we think about these modules? We should think as follows. Since we only can go up in the weight space a finite number of times because of condition 3, and because our modules are finitely generated, we should think of some vectors which are on top of the pyramid on which we can act with lowering operators. But if we take any vectors and we try to go up, we hit a wall at some point, and this is true for any vector. Moreover, any vector that we might choose can only be reached in a finite number of ways, and therefore this space is finite dimensional. This is how we can think of these modules. So this has a number of consequences. The weight spaces are all finite dimensionals. the weight space is a finite union of a given weight minus the lattice gamma generated by the negative roots. M is a finitely generated UN minus module. The center of the algebra only generates a finite dimensional space when it acts on a given vector. And there are further abstract consequences, like the fact that this category is Noetherian. That's a sort of a finite condition. It is abelian. We can define kernels and co-kernels, etc. It is closed under taking submodules, quotients, finite sums. And moreover, if we take a module and we tensor it with a finite dimensional module, then this operation of tensoring with a finite dimensional module is an exact functor. That is to say, it preserves short exact sequences in the category. So for now, let's recap. We're going to study representation theory of representations that look like this.